another talk today. We have Sarah Koch here from the University of Michigan talking to us about complex dynamics, the math BB real story.
All right, thanks very much, Adam. Thanks to Adam and the other organizers for inviting me here to share some of my mathematical work with you. Thanks also to the organizers. I've given them lots of headaches recently in terms of scheduling rearranges. In fact, I have to run out the door right after the talk to fly back to Michigan. My schedule's a little bit bananas these days, so I really appreciate the folks who I displaced in the original time slot of the schedule. Thank you for being flexible, and thanks to the organizers for moving stuff around for me this time. I appreciate that. Okay. So I'm very glad to be here today to talk a little bit about my mathematical research with you all. My research is in the area of complex dynamical systems, so we're going to get into exactly what that is. And in fact, we're not going to spend so much time in the complex world. We're going to be working with real variables instead. And then we'll complexify everything and bring things back home and get a sense of what's really going on. But while I have you here in this room as a captive audience, I'm going to start with one thing before we get to the math. Perhaps not. One thing about Zoom is that it's not letting me advance my slides. So we're I need somebody to jump in with a joke. Keep everybody busy for a second while we figure out how to do this. Oh, I have an idea. Yeah. There we go. Thanks. All right. So I'm part of the University of Michigan, and I work in the math department, and one of the most favorite parts of my job, one thing I absolutely love, is that I'm also involved in something called the Math Corps. The Math Corps is something absolutely phenomenal. It started in 1992 at Wayne State University in Detroit, Michigan. It's a free summer camp for middle school kids and high school mentors. So the kids show up, they're rising 7th graders, 8th graders, and 9th graders, and they work in teams with high schoolers. The high schoolers work with the younger kids, they work on math, they also bond, forming these older sibling, younger sibling kinds of relationships. So the Math Corps uses math to celebrate the greatness inside children, and it's a wonderful program. I found out about it accidentally about 6 years ago. I visited and I was completely blown away by what I saw. I started a Math Corps site together with my colleague and friend Stephen DeBacker at the University of Michigan. Our first year was in 2019. We ran a pilot program for 4 weeks. We had 40 middle school kids, 20 7th graders, 28th graders, and 20 high school kids in our camp for those 4 weeks. And in fact, Math Corps only meets Monday through Thursday. So that first iteration of that summer camp, we only saw the kids for 16 days. And up here, you can see pictures from our camp over various summers. I want to draw your attention to that graph with all the slopes in it. Every slope in that graph represents a middle school camper. The left end point represents their pre-test score, the score on the math test that they took when they entered camp. After 4 weeks, following the Math Corps curriculum and all the Math Corps principles and policies, we did everything we could. We did our best to follow that model from Detroit. The kids really improved their test scores. The average score tripled in 4 weeks. So the right end point of the segment represents the kids' post-test score after 4 weeks. So I was sold right then and there. I said, we have got to keep this program running, and part of the Math Corps magic is that kids grow up in the program. The 7th graders will be 8th graders the next summer, the 8th graders will be 9th graders the next summer, and then the 9th graders will be the next generation of high school teaching assistants teaching the new 7th graders. So the statistics, the data for the Detroit site, they've been running since 1992. 80 to 90% of the kids who grow up in that program will graduate from high school, and among those, 90% will go into college or to the military. So one point that I have in sharing this with you, I want to just emphasize that this program is extremely exportable. Detroit is very generous. They will give you all the resources you need, and you can start one. And there are several Math Corps sites that exist now, and they've been started in part because of people hearing about this incredible program just like you all, as an audience member. I now take the opportunity to share this with everybody when I get invited to do research talks or other kinds of talks. And some folks in the audience have been inspired, and then they contact me, and we get them in touch with the Detroit site, and then they start their own camp. So I'd be happy to talk with you more about this. It's an incredible, incredible program, and it makes the world a better place. Okay, So now let's get to the math that I'd like to discuss with you all. So we're talking about complex dynamics, the real story. So we're going to start with quadratic polynomials, and we all learned in school what a quadratic polynomial is, sort of as a function. I want to think of these polynomials, they're defined over the real numbers. I want to think of them as functions from R to R. So we all learned that the graph of a function like this is some kind of parabola. We learned that in school, and maybe we spent some time studying what happens when we scale our coefficients or we shift everything, how the parabola moves, what happens to the graph. But we learned about it, or at least I learned about it, as a very static object. You learn about this, and then you move on to learn about other conic sections. That's not what we're going to do today. We're going to exploit the fact that the domain and codomain of this function coincide, turning this into a dynamical system. This means that we can now iterate these functions. We can compose them with themselves over and over and over again and study what happens. So just in these two examples, x maps to x squared minus a quarter. We see the graph of the parabola up at the top. And x maps to x squared minus 5 halves. We see the graph at the bottom. I'm going to take the sixth iterate of each of these functions. I'm going to get some polynomial function of degree 2 to the 6, or 64, and I'm going to graph those for you over here on the right-hand side of the slide. So right now, just in the first couple of minutes of exploration here, you can see there's a very drastic difference between the shape of the red graph up at the top on the right and the shape of this more purpley graph down in the bottom on the right. What is responsible for that difference? What happened? The only thing that was different from the point of view of our original functions is that we changed the value of c. C is a real parameter, so for every real number I pick for c, I'm going to get a different quadratic polynomial that I can iterate. And then I want to try to understand things like this. There's something to understand just in this tiny experiment that we've done so far. So from the point of view of iteration, there are some natural subsets to look at. And those are subsets of the domain, or equivalently the codomain, that are invariant. So an example of an element of such a set would be the fixed point, a fixed point of the quadratic polynomial. So that is exactly a point in the space that is fixed by the function. So we can see graphically where our fixed points are. We just graph our parabola, which here is x squared minus a half, and then we draw the line y equals x. And we look at where it intersects our graph of our parabola, and then we have our x or y coordinates of our fixed points. So there are two fixed points of this function. One of those fixed points is attracting, this one on the left. One of those fixed points is repelling, this one on the right. I can tell that this one on the left is attracting because the slope of the curve at that fixed point has absolute value less than 1. So what does it mean to have a fixed point that's attracting? It means that there's a neighborhood of your fixed point on which, when you take points in that neighborhood, they're going to map strictly inside. That neighborhood maps strictly inside of itself under the function. The points are going to be attracted to the fixed point. A repelling fixed point, this one over here on the right, the slope of the curve is greater than 1 in absolute value. So if you take a point that's very close to this fixed point, it's going to be pushed away from the fixed point, and that's the repelling behavior. Okay, so we see we can have attracting fixed points. We can have repelling fixed points. Oh, and then this little black rectangle here, it's drawn in a very kind of small way. It's drawn to scale. I'll blow it up in a second. These white points, which I hope you can see, represents what's called the orbit of the point 0. So the orbit of a point in our space is the sequence, and that's the f and x naught. So we just look at the original point where we start, x naught, we plug it into our function, we take that output, we plug that back in, we take that output, we plug that back in, etc. That's called the orbit of the initial point. So here in white, you can see, here I've blown up that black rectangle, the orbit of 0. So we start here at x equals 0, we plug it into our function, which is x squared minus a half. The output is over here at minus a half. We take that, plug it in, we get this, we take that, we plug it in, we get that, and it bounces back and forth until you can see that orbit of 0, that sequence is going to converge to the attracting fixed point. Okay. This black rectangle will become important for us in a couple of slides, so I'm going to refer to it again. All right. So here's another parabola for our collection, x squared minus 10 ninths. Both of the fixed points here are repelling. We just look at the slope of the curve at those fixed points. So we don't have any attracting fixed points, but in fact we have something else. We have an attracting cycle of period 2. So a cycle of period 2 is just a collection of 2 points that are exchanged by the function, and then it's attracting, if there's an open neighborhood that's attracted, of points that are attracted to that cycle of period 2. And you can kind of see, let's see, how could we find that? So let's start again here at 0. We plug 0 into our function, so we go down to where we hit the parabola over here, and now we want to take this output point and plug it back into our function. One way to do that is to project over to the line y equals x. The x and y coordinates here coincide. We know that the y coordinate was the output of our function. We take the x coordinate there, which is equal to the y coordinate, and plug it into our graph, our function. We get this output point, and then we keep going. And you can see there is, in fact, a cycle of period 2 here, and it will attract an open set of points. It's an attracting cycle. We don't have any attracting fixed points, but we have an attracting cycle of period 2. This guy over here, there are 2 fixed points. We can see them, the intersections of the line y equals x with our parabola. They are both repelling, and in fact, this function has no attracting cycles at all. Okay, so we really have this kind of zoo of sorts of different behaviors to understand in just this handful of examples. So as mathematicians, how would we understand what we've seen so far? How would we catalog it? So here's one idea. As we adjust this real parameter c, we can try to keep track of what happens. So here, when c is negative 5 halves, we have no attracting cycles. When c is negative 10 ninths, we have 1 attracting cycle of period 2. And when c was negative 1 half, we have 1 attracting fixed point, or a cycle of period 1. So how are we going to understand the different kinds of behavior that we get as we adjust that parameter c? There's a lot of stuff to understand. We're going to appeal to a theorem that's about 100 years old. This is a theorem in complex dynamics, but it applies here as well, because we can think of these real polynomials as living over the complexes. Right? A real number is also a complex number. Okay, so we can apply this theorem, and this theorem says, it's due to phi 2, if there is an attracting cycle, then it must attract a critical point. If we look at our polynomials in degree 2, there is a unique critical point. And that critical point in our coordinates is that x is equal to 0. And so if there's an attracting cycle, then necessarily 0 will find it. The orbit of 0 will be attracted to that cycle by this theorem. So we're going to cache this theorem in and use it to help understand kind of how to catalog or record the different kinds of behavior that these functions have. That is, are there attracting cycles, yes or no? This theorem says all you have to do is compute a single orbit, the orbit of 0. And here's the orbit of 0 written as a function of c. 0, when you plug it in, maps to c. c, when you plug it into your function, maps to c squared plus c, etc. That's the orbit of 0. So all we have to do to figure out if there's an attracting cycle for your favorite value of c, for x squared plus c, is compute this orbit and see what it does. Okay, we're going to actually restrict our attention to the c values between -2 and 0. You can prove with some complex analysis that if you take a c value that's less than -2, the orbit of 0 is unbounded, and therefore there are no attracting cycles. So we're going to toss those out. So we're going to ask what happens as c runs in this interval. Do we have an attracting cycle, yes or no? And then how do we figure out sort of what kinds of things to draw or understand? Like, what does an answer to this question actually look like? here is a candidate way to sort of think about it, or maybe an experiment that we could run as mathematicians. So we're interested in the c values for -2 to 0. And we want to take a particular value of c, and we want to compute the orbit of the critical point, just like we talked about on the last slide. And I want to know, does that sequence converge to an attracting cycle for a given value of c? Okay, so here's one way to maybe track that. In one of our examples, we had the value c equals -1/2, which is right here on the c-axis. And above that value, I've drawn a blue vertical line. That blue vertical line is supposed to indicate, is supposed to be this domain of this function. So that's where the orbit of the critical point lives. It's naturally a subset of the domain space. So what I'm going to do is I'm going to compute this critical orbit, maybe 20,000 terms of it. But then the question I'm asking is, does that orbit converge to an attracting cycle? So I actually don't care about the initial part of the orbit. I only want to compute 20,000 terms and then grab maybe the last 1,000 of them. I'm going to take those data points and then plot them vertically above that value of c. So I'm plotting the set of accumulation for the critical orbit. So since this is a c value, c equals -1/2, where there's an attracting fixed point, I know that that set of accumulation has to be the fixed point that that sequence converges to. So here, I'll illustrate it with our rectangle. There's our black rectangle from the example before. The white dots are the orbit of 0. But remember, we don't want the whole orbit. I'm going to toss out the first 19,000 points. And the point I'm going to be left with is the actual location of the attracting fixed point inside the interval -2 to 2. That fixed point is located there, wherever that number is. Is that clear? Okay. And now what we're going to do is play the same game with every value of c. I'm going to draw that blue vertical line, compute a huge number of points in the critical orbit, and just grab the last 1,000, plot them for you. So let's do it. Let's move c closer to 0. If you move c closer to 0, for all of these points, we draw the vertical line, we draw the accumulation set for the critical orbit, it'll just be a single point. All of these c values will give you an x² plus c where there's an attracting fixed point. Great. There's another example we had, -10/9, x² minus 10/9. There was an attracting cycle of period 2. We do the same thing. The accumulation set of the critical orbit is that attracting cycle, and there's the location. So something happened. Something happened here. Okay, what? You can do this. This is a very computer-friendly experiment. We could all just do this right now and draw what happened. Get the data. This is what happened. So something kind of incredible happened. For these c values over here, where there's just this tail, x² plus c has an attracting cycle of period 1. At some special c value right here, that cycle explodes into a cycle of period 2. And then that becomes attracting. This point here is called a bifurcation. Interesting. So then we can grab another c value, this one right here. We did not see this in our initial examples. It's an extra one. There's an attracting cycle of period 4, and there are the points. What happened in between this region and this region? The same thing. This arm of the 2 cycle explodes into 2 more. This arm of the 2 cycle explodes into 2 more, and you have more bifurcations. So what's going to happen next? The same thing is going to happen. Each of these arms is going to explode and bifurcate. So the next period of the cycle, we went from 1 to 2 to 4 to, thank you, to 8. and then to 16, and then to 32, etc. This is called the period doubling cascade. So these C values will keep bifurcating, the picture will keep bifurcating, and you can keep going until you get this picture. Okay. So this picture is fantastically complicated, but it's not hard to draw. You all already know how to draw it. This is called the bifurcation diagram because it's full of lots and lots of bifurcations. It's been on the scene for decades, for a good long time. It naturally shows up in differential equations when one studies something called a logistic map. That's not a coincidence. There are connections to what I'm telling you about today. So we have this sort of fixed point, the attracting fixed point region, attracting cycle period 2, attracting cycle period 4, etc. And then there are lots and lots of mysterious things that happen in here, lots of things where I have no idea what's happening. There's a lot to unpack. And just those sort of seemingly innocent quadratic polynomials that we all learned about in school gave us this picture. All right, let's explore this a little bit more. Here, you can see there's a region of calm. See, this picture is kind of fantastic. It's very busy, and then it calms down into this little, like, calm, stable region. And then it gets very busy, and then it calms down into these ribbons of stability. So what are those stable regions? Those stable regions arise whenever you have an attracting cycle. So here I have this stable region, this area of calm, this little window, and there are 3 points right here. There's an attracting cycle of period 3 for this particular C value. So let's explore the picture a little bit more. That pink rectangle, we're going to zoom in, and you see this. Please notice you have more regions of calm where there's an attracting cycle of some period, and then anywhere where you used to have some kind of arm coming in, there's going to be a bifurcation. So what that means is you see small copies of the same picture inside of itself at every single scale. So this picture is self-similar in a very strong sense. If I zoom into any part of the picture, we're going to find a region of calm, and we're going to find a tiny model of bifurcation. Okay, so one question I'd like to pose to the group, maybe to explore for the next part of the talk, is how do we understand these regions of stability, these regions of calm in this picture? They're sort of absolutely everywhere. What are some things that we could do? Well, one thing we could do, as we've already discussed, is we can label these regions of calm with integers. Like there's a 1 here corresponding to the period of the attracting cycle. There's a 2 here. There's a 4 here. There's an 8 here. So every region of calm gets its own integer. So we could try to figure out how those integers are kind of placed in this picture. Is there any kind of structure to that? So that's one thing we could do. Another thing we could do to try to understand these regions of stability is to take advantage of another theorem in complex dynamics that asserts that every single one of these regions contains a unique value of C, that uniqueness is important, for which the critical point is actually in the periodic cycle itself. So it's not only that there's an attracting cycle and the critical point is attracted to it, but at some special C values, the critical point is actually in the cycle itself. So what we can do is leverage this uniqueness and label each one of these regions of calm somehow with some data that corresponds to what it means for that critical point to be in the cycle itself. So we're going to now explore that connection a little bit. Questions? Yes?
Yes. Shading is like measuring of the accumulation.
Sorry, I can't hear you.
Yeah, I was wondering like the shading is measuring of the accumulation, like the impact.
Yes, exactly. So the question is about the shading, what's responsible for the different shades. The different shading corresponds to, it's darker where there's more data. So this picture was drawn with a computer in a way that I outlined. I lied a little bit about the exact numbers that were being used to construct it, but it's darker where there's more computer data. So that's the shading in the picture. Yeah?
How do you know when to stop iterating?
That's a great question too. How do you know when to stop iterating, right? So I said that if there's an attracting cycle, the critical orbit will find it. So maybe to generate this picture, we did 20,000 steps of our critical orbit, but there's an attracting cycle of period 68,000. So you don't. You don't know when to stop iterating. This is just giving us some kind of computer picture that we're going to try to explore, get some questions, and then prove some things about. But that's a great question. There's data missing in here for sure because of the limitations of computers and how I drew it. More questions? Yes. Yes. So the question was, when you have this bifurcation, does it happen at the same value of C? So you'll notice here, if I were able to draw a vertical line here, there would be a vertical line connecting this point to this point, and it would correspond to the same values. Yes? More questions? Yes. Is there a formula for this C's? Yes, so I can actually write down some equations that define the C's for you. So those places where the bifurcations happen, they happen at sort of an algebraic condition or for those. So I can tell you where those happen. There are countably infinitely many of them, and they're solutions to some almost polynomial equations. More questions? Okay, yes.
I see like some stars horizontally in the middle of the picture.
Yes.
0? Why 0?
Yes, so these dots here, you're asking about these dots right here. What's the significance of those dots? And you can see them repeated in this picture in lots of places. I'm not entirely sure because I'm not the one who drew this picture. So I think that that's an artifact of the data, but if I thought about it maybe for 5 minutes more, I might have another explanation for you. So I'm not sure. More questions? Okay. There are also these beautiful curves in this picture. Do you guys see these? These are polynomial curves. And if you look, you can sort of see why. Look at this orbit. The points in this critical orbit are all polynomials in C. If you take any one of those polynomials that show up in that orbit and plot it, those are those curves. Those are those curves. And those curves, the collection of all infinitely many of those curves, will approximate this picture. So that's an algebraic approximation to this extremely complicated fractal. Okay. All right, so as I said, we want to understand these regions of calm, these regions of stability, and we're going to exploit this purple fact. Each region contains a unique value of C for which the critical point is periodic. So we're going to focus in on this period 3 region right here. There's one value of C in that little stable region where the critical point is periodic. Let's grab it. Here it is. So this is a real quadratic polynomial of the form x squared plus c, for which 0 is in a cycle of period 3. And I've drawn with this green polygon some kind of picture to help us see that orbit of 0. 0 maps down here to this y value. We project over to the line y equals x. We take the x coordinate, plug it in. We get this y value, project over, plug it in. You do get 0. Period 3. Okay. What I'm going to do, instead of thinking about the graphs, is I want to encode that polynomial with some data that's easier for me to understand, sort of a minimal amount of data. So what was important? What's the thing I'm going to grab? I'm going to grab the 3. 0 is periodic of period 3. The critical point at 0 is represented with a star. The star maps to its critical value, which is a pink dot. The pink dot maps to some blue dot, and that blue dot maps back to the star. So this is, I'm going to call this a cartoon. This is encoding the dynamics of how 0 maps around and then closes up. So the relative order of the points is important and how they map to each other. That's the only data that's important. And I'm encoding that with a cartoon. So this cartoon encodes that polynomial. Period 3. Period 4. There are 2 polynomials of the form x squared plus c, c real, for which the critical point 0 is periodic with period 4. There's this one over here, where the critical point maps to its critical value maps to its image, that image maps here, and then that guy closes up the orbit, period 4. Then there's this cartoon. The critical point maps to its critical value, that maps back over here, that maps in between the critical point and the pink dot, and that closes up. So these cartoons are different shapes. They're different polynomials. So there's 2 polynomials for period 4, 1 for period 3. Period 5, there are 3, and you can encode them with the various cartoons. So it doesn't take a mathematician to maybe guess what happens next. So we had period 3, we had 1. Period 4, we had 2. Period 5, we had 3. It doesn't continue like that. It gets much more complicated. Okay. So for period 5, there are 3 quadratic polynomials where the critical point is periodic at period 5. And those are all encoded with these cartoons. Okay. So here's just a summary of our data so far. 1, 2, 3. Okay. So remember, our original problem was to take that very complicated bifurcation picture, try to understand those regions of calm. I promised you that every single region of calm could be labeled uniquely with a quadratic polynomial where the critical point was periodic. So we can use these cartoons to help us label those regions. If we could only understand which cartoons arise. If I give you a cartoon corresponding to period 67, that's going to be some permutation, some cyclic permutation of 67 points on a line. One of them's a star, one of them's a pink dot, and the rest of the points are mapping around in a cycle. Can you tell me if it arises from an x squared plus c? Can we understand which cartoons arise? Good question. Oh, okay. So this is the break in the talk where it's time for a magic trick. Not really. But I want to point out that the permutations that are encoded in these cartoons correspond to a very particular way of shuffling cards. It's called Gilbreth shuffles. So here's what a Gilbreth shuffle is. You take your deck of cards, and your friend gives you a number between 1 and 52. I'll go with 13 because it's smaller. There you go. Thank you. 1, so now I'm going to deal off the top. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so now I have the 2 parts of the deck, and now I riffle shuffle them. The permutation on the deck of cards is called the Gilbreth shuffle. The Gilbreth shuffles that are cyclic, meaning there's only one cycle, those are exactly the permutations that show up in the card tricks. This is really cool. You should, if you like this, if you like magic, I love card tricks. Google Percy Diaconus. Percy Diaconus and Roland Graham. And the title of, they wrote a book about, they have lots of books together, but the book I'm thinking of has a chapter called From Card Shuffles to the Mandelbrot set. So I think their chapter is available for free. Princeton University Press, it's awesome. Okay, so which cartoons arise? That's a question we're interested in. You can develop the Gilbreth shuffles into some cool card tricks. Okay, so let's see if we can come up with a conjecture about which cartoons arise. These are exactly the cartoons that are encoding the quadratic polynomials of the form x squared plus c, where the critical point is in a periodic cycle. So let's just make some observations. So you can see in every single one of these cartoons, the critical value is the furthest most point to the left. It's always on the left. Does anybody have an idea about why that might be? Yes?
The global minimum quadratic.
That's right, it's the global minimum. That's right, our quadratic polynomials open up. The critical value is the minimum of the function, so it will always be the point furthest to the left. And in fact, you can work out with a little bit of algebra that the image of the critical value will be the point that's furthest to the right. So those conditions are necessary. Critical value is furthest to the left, its image is furthest to the right, and then the question is, what happens in the middle? How does it wrap up? Another necessary condition is monotonicity. Our parabolas open upwards. So on the left, they're decreasing. On the right, they're increasing. And what that means is that if we take 2 points, like here in this example, that are to the left of our critical value, our function should be decreasing there. So their relative images should swap. So the pink point is to the left of the blue point. When I look at their images, the image of the blue point is here, the image of the pink point is here, the relative positions swap because there is decreasing. So if you take the monotonicity into account and the extreme points, namely the critical value on the left, its image on the right, those conditions are all necessary for our cartoons. And they're also sufficient. So this is a very deep theorem of Bill Thurston's, and its first incarnation is in a paper by Milner and Thurston called On Iterated Maps of the Interval, which was published, I think, in the late 70s or early 80s. So what their theorem tells us, Thurston's theorem in particular, tells us that if we draw a cartoon that satisfies just these two criteria about critical value is the furthest one over here, its image is the furthest one over here, and we wrap up that cyclic orbit in a way so that the monotonicity of our parabola, decreasing and then increasing, is preserved, it will be realized by a quadratic polynomial of the form x squared plus c. So Thurston's theorem inside that paper tells us exactly which cartoons arise. So what this means is we can label all of our regions of calm with these cartoons. We know exactly which ones to look for. You can program these conditions into a computer and figure it out. Okay, so I'll state this more formally here. This is not exactly how Thurston stated it. Every admissible cartoon, meaning satisfies those conditions, those necessary conditions, corresponds to exactly one polynomial. So it corresponds to one and only one polynomial, that uniqueness that we're leveraging. So let's just keep track of what we've done so far. The number of cartoons of a period n is equal to the number of quadratic polynomials of the form x squared plus c, so that 0 is periodic of period n. Why did we even ask about that to begin with? Well, because of this condition, that number is equal to the number of stability regions in our complicated picture. That's where we are so far in the talk. Okay, so one way to label our stability regions is with the Thurston cartoons, but I'd actually, right now, like to switch gears and propose a more algebraic approach. I actually like the cartoons, that's my favorite way of doing it, but the algebra is awfully beautiful too. So we're going to think about this question from an algebraic point of view. Okay, how do you figure out how many polynomials of the form x squared plus c there are so that 0 is periodic of, say, period 17? How would you do that? Here's one way to do it. So up at the top is that critical orbit that we've seen so much of. And say I'm interested in, I'll draw the critical orbit here. Okay, say we're interested in values of c for which 0 is in a cycle of period 3. What would we do? Well, 1, 2, 3. We're going to grab this point in the orbit, and we want this to be equal to 0, because then 0 is in a cycle of period 3. So setting this equal to 0, we can find c values for which 0 is in a cycle of period 3 by design. But it's not exactly right. There are some degenerate solutions, namely c equals 0, that I don't want. So I'm going to get rid of that one. Because c equals 0, the critical point would be fixed. I don't want that one on period 3. Okay, so just using the critical orbit, what we can do is write down polynomial conditions on the perimeter C so that the roots of those polynomials correspond to C values for which 0 is in a cycle of the right period. So these are called Gleason polynomials. The Gleason polynomial for period 1 is just the polynomial C. Its root is at c equals 0. If c equals 0, x squared plus c is very special in that 0, the critical point, is periodic period 1. The second Gleason polynomial for period 2 is c plus 1. The root of that is at c equals minus 1. X squared minus 1 has the special property that 0 is in a cycle of period 2 by design. Here's the third Gleason polynomial. The roots of this are exactly the c values for which 0 is in a cycle of period 3. There's the fourth, there's the fifth, and so on. These just come from the critical orbit. Okay. So what we're interested in our real story of complex dynamics, is we want the real values of c, we want the real roots of these polynomials. Those are the c values that we want, that we're going to use to understand our very complicated bifurcation picture. Here's a question for those of you who are algebra fans. If I give you a collection of polynomials, like the Gleason polynomials, how do you decide, how do you figure out how many real roots they have? Let's make some observations. These polynomials are all monic, and they're defined over the integers. Andrew Gleason, whom they're named after, was working at Harvard back in the early 80s. I didn't know him, but I heard he was a very good problem solver. John Hubbard, who was my thesis advisor, who was visiting Harvard at the time, working on some of this math. And Hubbard ran down the hall to Andrew Gleason and showed him these polynomials and said, "What can you tell me about these?" And Andrew Gleason, in like 5 seconds, said, "They have simple roots." They do. I would not have gotten that in about 5 seconds. So Gleason had this very clever argument looking at the discriminant and proving it was non-zero, looking at the discriminant mod 2. Okay, so that proves that the roots are simple. Every person who we sort of introduce these to, who particularly likes polynomials, always asks us this. Are they irreducible over the integers? I would love to know the answer. We have no clue. We've tested this up to degree like 22, and so far they are, but we don't know if they factor. And I have no idea how to approach that problem. It seems very difficult. Okay, so these Gleason polynomials, they're real roots. These are the things that we're after. We want the real roots of them. How do we figure out how many real roots they have? We don't know how they factor. We don't know if they factor. If I give you a collection of polynomials and I ask you about their roots, what's one thing you could do? You could take the complex plane, here comes the complex part, and just plot the roots, all on the same copy of the plane. So let's do that. So we're going to take a complex plane, take all these Gleason polynomials, they're infinitely many, and just plot all their roots. We want to know which are the real ones. So let's do that. Okay. This is my favorite part of the talk. People are like, oh, who invited that? Okay. So you get this absolutely incredible and probably familiar object. All right, so let's just double check with what we're actually seeing. So here is a big blob at c equals 0. That's the root of the first Gleason polynomial. Here's a big blob at c equals -1. That's the root of the second Gleason polynomial. And then the third Gleason polynomial has degree 3. So there are 3 roots. There's one real one, corresponding to our real cartoon. And there's a pair of complex conjugate ones here, etc. So that's what you're looking at. Okay, so you might recognize this. All right, so in walks the Mandelbrot set. Okay, so if we're going to complexify our variables, so I'm going to emphasize that by using the variable z instead of x for the variable in my polynomials. C is now a complex parameter. So it's allowed to be any complex number. The Mandelbrot set is a subset of that parameter space. What subset is it? It's the set of all complex numbers, little c, so that the orbit of 0, that critical orbit again, just playing an important rule, the orbit of 0 is bounded under iteration. So in particular, we were doing real dynamics. We can skewer this picture here. The real axis is right here. We're interested in the real parameters. So if we have an attracting cycle for, say, a real value of c, then that real value of c has to live inside the Mandelbrot set, right? Because we know that if there's an attracting cycle, the critical orbit will find it under iteration, and therefore that critical orbit is bounded. So all of the c values we want are in the real axis in this picture inside the Mandelbrot set. We want those c values where there's an attracting cycle. So just so you get your bearings, the tip of the tail here is at -2 on the real axis. This cusp is at 1/4. 0 is about right here. Why is this picture symmetric with respect to complex conjugation? It comes right from this definition. So the orbit of 0 is bounded under z squared plus c if and only if it's bounded under z squared plus c bar. That's why it's symmetric this way. What do I know about this? This set is compact. It's not empty. And I know that it's connected. The theorem that it's connected is due to John Hubbard and Adrien Duodie back in the early 80s. That argument that it's connected is absolutely incredible. It's a really beautiful piece of mathematics that complex analysis graduate students could understand. It's nothing fancy, it's a complex analysis. We do not know if the Mandelbrot set is locally connected. That is a very hard problem that people are still working on. They've been working on it for decades, and some folks, at least one, progress on that problem has led to at least one field spill. So this seems to be quite difficult. The Mandelbrot set is locally connected if and only if a certain conformal map on its complement extends continuously over the boundary. Which means we have to understand the boundary better to settle this question of local connectivity. Here's something pretty cool that ties this back to our Gleason roots. Kurt McMullen proved that if you take the topological closure, the analytic topology, of the roots of the Gleason polynomials, it will contain that mysterious boundary from the So those Gleason polynomials, their roots are this collection of algebraic integers. The topological closure of that collection of algebraic integers somehow knows about this extremely complicated. Okay, so let's just check in here a little bit with the complex side of things. They have the best pictures, in my opinion. So here's the third Gleason polynomial. By design, the three roots of this polynomial will correspond exactly to those c values for which z squared plus c, for which the critical point at 0 is periodic with period 3 under z squared plus c. Here is 0, the center of each of these pictures. There's one c value right there. 0 here you can see is in a cycle of period 3. I've tried to indicate that with the white stick figure. Here it is down here for another value of c, this one that lives here. And here there's a real one, which we expect, because that's what we saw. This corresponds exactly to our cartoon. 0 maps over here, this maps back, and then it closes up, period 3. Okay. I can't give this talk without sharing the silly names. It's part of the fun of the subject. I'm not responsible for any of them, by the way. The yellow guy on the top, that's called the rabbit because it has 2 ears. The green, the reflection, is called the co-rabbit, of course. And the red on the left, that's the airplane flying at you out of it. So many of these Julia sets have lots of names. Hubbard would tell you they're all old friends of his, and it makes kind of studying the subject fun, and they're very useful, these names. Of course, because I can't remember exactly what value of c this is, but I do know if somebody says rabbit, I know exactly what they're talking about. Okay. All right. So now that we're working over the complex, we can look at all the roots of the Gleason polynomials. Remember, we care most about the real ones, but let's just think about all of them at once. Maybe we'll see some structure there that we couldn't see before. So we can label each one of these connected components of the interior of the Mandelbrot set with an integer that corresponds to the period of the attracting cycle that this corresponds to. So just very quickly, if you take a C value from this heart-shaped region and you look at C squared plus C, there'll be an attracting cycle of period 1. That's what this 1 means. If you take a C value from this connected component of the interior of the Mandelbrot set and you look at C squared plus C, there'll be an attracting cycle of period 2. That's what this 2 means. So the root of this Gleason polynomial at C equals -1 is right here in this 2 ball right here. This root of this first Gleason polynomial is right here in the main cardioid because there's a 1 there. So this number is the period corresponding to the attracting cycle, and in fact can be used to label the whole component. So the third Gleason polynomial, there are 3 roots. There's 1 here on the real axis, and then these 2 here. So this component is a 3, this component is a 3, this component is a 3. The fourth Gleason polynomial has degree 6 over the complex numbers. There are 2 real roots. We saw that in our cartoons right here, and then there are 4 other ones. 1, 2, 3, 4, 2 pairs of complex conjugates. So you can label all of these components with integers exactly the same way we were labeling those stable regions with integers when we were doing the real step. It's the same phenomenon, and in fact, they line up at exactly the right place. So remember, this was period 1, that lines up exactly over this component in the complex. Then it went bifurcated into period 2. Those real C values where these bifurcations occur are at exactly these points here. Then that bifurcates to period 4, period 8, etc. Remember this period 3 window in our bifurcation diagram? That corresponds to a teeny tiny baby Mandelbrot set on the real axis of period 3. Okay, so if you zoom into the real axis, which is pretty fun, I don't think I have time to do that with you guys today, but I highly recommend doing it. Zooming in actually anywhere in the Mandelbrot set. So if we zoom in, say around here, we're going to find small copies of the Mandelbrot set inside of itself at arbitrarily small scales. This is the same phenomenon that we saw over the real numbers when we were looking at that bifurcation diagram. We saw those regions of calm. We zoomed into the pink rectangle and we saw more regions of calm and more copies of the bifurcation diagram. We were to keep zooming in, we would see the same thing. In the complexes, what that looks like is baby Mandelbrot sets everywhere. Okay, so let me just finish up here and tell you what I've done for this project. So we have these Gleason polynomials. We're interested in the number of real roots of these polynomials because those correspond to ways that we can label the regions of calm in our bifurcation picture. I told you that we don't know if the Gleason polynomials are irreducible. So one thing one might do that seems kind of natural, well, if you don't know if they factor over the integers, you can factor them on 2. 2 is prime, 2 is also the degree of our polynomials, so it's a natural choice. So we can factor each of these polynomials. One thing that really kind of knocked us off our chairs is that these numbers are the same. The number of real roots the Gleason polynomials have coincides with the number of irreducible factors that you get when you factor them over the field as well. And the proof is not satisfying. The proof is you count. You count irreducible factors mod 2, you get some expression. You can count the number of real roots through one of these like Thurston mechanisms, and those 2 counts match. I don't have a natural bijection from one set of objects to the other. And I don't know if there is. It's very mysterious and kind of tantalizing that this thing is true at all. So here's just an instance of our theorem. Here's the third Gleason polynomial. We know there's one value of C given by this, the polynomial is given by this cartoon, for which 0 is periodic of period 3. If you factor this guy mod 2, you get one irreducible factor. Here's the fourth Gleason polynomial. We know there are 2 admissible cartoons, 2 polynomials of the form x squared plus c, c real, for which 0 is periodic of period 4. This splits into 2 irreducible pieces. Here's the fifth one, it splits into 3 irreducible pieces, and there are the 3 cartoons. So it would be really great if I could point at this and say, this cartoon corresponds to this factor. I don't know how to do that. I'm lying just a little bit, but I don't have a complete understanding of how to do that. And I think it's kind of a really fun thing to think about. How could this just be like the same count on both sides? There should be something to say, and we don't know what it is. Okay, and skip this. So now just to sum up, and then I'll stop. So we started with real polynomials. We want to understand the regions of stability in this picture. We used some old theorems that said what you should really do is count the number of real roots of the Gleason polynomials of that period, because every one of those regions contains a unique C-value where the critical point is periodic at period n, and then eventually at the end of the talk, we arrived here where that number of real roots coincides with the number of irreducible factors of those Gleason polynomials mod 2. So that sort of fits into this grand scheme of things in the real sense, the real complex dynamic sense. I think I'm just about out of time. So this is the way we end everything in the math core. We have to be dismissed. And so we say, have a beautiful day by creating a beautiful day. Thank you. Well, it's prime, and it's natural from the point of view of the degree of our polynomials. So that sort of was the reason. Like if we were doing cubics, I would have picked 3. If we were doing quartics, I would have to think a little bit harder. It's because of where things are coming from, sort of, and the way that this is all working with these quadratic factors in here. So 2 is sort of like presenting itself in a lot of these constructions as an important number, and it turns out that it did the trick. There's probably some better answers to that. Somebody who does number theory might have maybe see some other connections here as to why 2 is a best guess. But here it just kind of presents itself in the context of the question as a good thing to try. It's what Gleason used in his proof, exactly. It's what Gleason used in his proof to show that the discriminant was non-zero. He looked at the polynomials and proved mod 2 that it was non-zero. It's because of where the critical orbit polynomials come from. You can sort of see the 2 kind of like staring you in the face. More questions? Yeah.
Given who wrote the Milner-Thurston paper, is there any topology?
Is there any topology? Yes, there's a lot of topology. So it's a paper by Milner and Thurston and 2 of the great topologists. Yes, so there's a ton of topology in that paper, and in fact, we sort of saw it, right? Like, I was using these cartoons, which are very sort of floppy objects. The only relevant data here is not the exact position of the points, it's the relative order and then the arrows on how they're mapping around. So that's a very Thurston-y thing, Thurston construction to look at. So there's a lot of topology here, and the Thurston theorem I quoted is just one instance of maybe one of the most important theorems in my subject, which is called Thurston's topological characterization of rational functions, which says that if you're presented with some floppy topological object, which looks like a branch cover of a sphere in some way, sometimes it has a natural rigid geometry, and the way one solves that problem is by iterating on a type Moore space. And so this is an instance of that theorem, and this cartoon is exactly encoding that topological class up to what we would call Thurston equivalence. So yes, there's a lot of great stuff in that paper. More questions? Yes? So the question was, is there a connection between Fourier analysis and the boundary of the Mandelbrot set? I can show you that I hope everybody can still see. This is fractal stream. It was written by my friend Matt Noonan when we were in graduate school. And I use it all the time. And it has this quirk that it likes to crash, especially when you're given a presentation. So fingers crossed. I need to change the color so you all can see. Okay, so this is the Mandelbrot set, and it has a bunch of connected components of its interior that we've sort of talked about already. We bump up the iterations so that the picture gets sharper. Yeah, so these connected components that have a unique root of the Gleason polynomials in them. So the components where the parameters correspond to attracting cycles. You can write down algebraic equations for their boundaries corresponding to the cycle that is attracting. It gets less and less attracting the closer you get to the boundary. And then when what's called the multiplier of that cycle is equal to 1 in absolute value, that's when you're crossing these boundaries. So those are the algebraic conditions that come in here. It's that the absolute value of some complex number that's encoding how the cycle is behaving is equal to 1. And those will give you these boundary pieces. So if you're talking about series, the only series connection I can think of at the moment is the complement here. You can explicitly write down, those of you who remember your complex analysis, so you can take the closed unit disk and take its complement, and then you can take the complement of the Mandelbrot set. Okay. You can, it's kind of amazing, you can write down explicitly a conformal map, an isomorphism, from the complement of the closed unit disk to the complement of the Mandelbrot set. You can write it down. And if you remember your complex analysis, you put the Mandelbrot set on pause, and I gave you a rectangle and asked you to do the same thing, to write down a conformal isomorphism from the complement of the closed unit disk to the complement of this rectangle, you would have a really hard time. It's hard to do that. But somehow, using where this comes from, the dynamics, you can be explicit and write out the exact form, the Riemann map from the complement here to the complement here. And so that is a holomorphic map. And as I mentioned, we don't know if the Mandelbrot set is locally connected. It's locally connected if and only if that Riemann map extends continuously to the boundary. In a sense, which would make more sense if we're going this way, but I'll shove that under the curve for now. So because it's holomorphic and because we want to know if it extends continuously over the boundary, you can look at its series and then see what it's actually doing, its Taylor series there, and study the coefficients and see if they converge to anything meaningful. That's the extent to which I've encountered series here with this guy and the boundary. More questions? Yes?
Does something different happen if the coefficient of x squared was negative in like the real case?
That's a great question.
I understand in the complex case then roughly the same.
That's a great question, right. So we seem to be taking some liberties here with our coordinates. Yes, so we're very much using this. So more generally, we could have taken something with 3 coefficients. But because we're doing dynamics, we're allowed to sort of mod out by change of coordinates in the domain and codomain simultaneously. So we're actually modding out by affine transformations. So that will kill 2 of the 3 parameters and leave us with just 1. So any quadratic polynomial that you give me, I can conjugate to a unique one of this form. And that's why we're going to go with just these. But you could change coordinates if you'd like and work with a different model. You get exactly the same kind of picture.
All right, so let's say